During this video, you will learn about a score designed to aggregate expert opinions when the elicitation of statistical dependency is relevant. During previous modules, you learned how experts' performance can be objectively measured with a classical model by using the statistical accuracy or calibration score and the information score. These are, however, not sufficient when measuring experts' performance in assessing probabilistic dependence. But first, what is probabilistic dependence? Well, suppose you want to know something about the probabilistic relationship between weight and length in children not older than 12 years. Experts could be asked questions such as, suppose you take a random member of this population, what is the probability that her weight would be larger than 20 kilograms, given that you know her length is more than 1.3 meters? Alternatively, instead of asking some probabilistic statement between these variables, you could ask directly or indirectly a correlation coefficient between the variables. With questions similar to this, we can measure experts' accuracy in assessing dependence. Consider an example with 3 experts, which has been used previously in this course. Expert 1 has a poor statistical accuracy, but is very informative. Expert 2 is more statistically accurate, but less informative, whereas expert 3 is quite informative and somewhat statistically accurate. In this example, expert 3 has the highest combined score, and her judgments would receive a higher weight according to Cook's method. However, the 4th column in this table indicates that the best expert according to Cook's method presents the second lowest dependence accuracy score, while the expert with lowest combined score in Cook's sense presents the highest score when eliciting dependence. What is thus the dependence accuracy score? Why does it matter to have a dependence accuracy score? Suppose we have a model for statistical dependence between 3 random variables. Such a model could be graphically represented as a figure on the right. The quantitative information regarding dependence could be summarized with the correlation matrix on the left. That is, the correlation between random variables 1 and 2 is about 0.9, the correlation between variable 1 and 3 is about 0.51, and the correlation between variables 2 and 3 is about 0.79. Similarly, as in Cook's method, we will have a correlation matrix that will be used for measuring the accuracy of experts when estimating dependence, a seed correlation matrix, if you will. Suppose that 3 experts have provided estimates of dependence. Notice that expert 1 misses the value of the seed correlation matrix on one element, that is, the dependence between random variable 2 and 3. And the remaining 2 correlations are perfectly estimated. Expert 2 is close in one element to the matrix, while expert 3 seems to be far from the seed matrix. Which expert do you think has provided more accurate estimates of dependence with respect to the seed calibration matrix? Inspired by previous results about correlation matrices, one may think that perhaps a difference between the determinants of the seed correlation matrix and those estimated by experts is a good measure of experts' performance on dependence assessment. After all, the determinant of a correlation matrix is 1 if all variables are independent of each other, and it is 0 if there is a linear combination between any pair of variables in the correlation matrix. However, after taking a closer look, one realizes that this is not a good measure. In our example, all correlation matrices have the same determinant. Instead, we use a function of the determinants of the correlation matrices. This function we call the dependence calibration score, and it is defined as 1 minus the Heilinger distance between experts' correlation matrix and the seed correlation matrix. The Heilinger distance is determined by the phi function defined below. This score has some nice properties. Firstly, its maximum value is 1, which happens when an expert captures exactly the seed calibration matrix. Its minimum value is 0, which is attained when a linear combination of any pair of seed variables is observed in the seed calibration matrix and an expert fails to observe it, or vice versa. It gets larger when element-wise the expert matrix approaches the calibration matrix. Finally, it gets smaller when element-wise the expert's correlation matrix departs from the calibration correlation matrix. Going back to our example, we may see that the dependence calibration score is about twice as large for expert 1 than for experts 2 and 3. We may use this score similarly as in Cook's model in order to combine experts' assessments of dependence into a decision maker dependence model. Any linear combination of correlation matrices will result in a correlation matrix. This means that the weights of the linear combination, similar as in Cook's method, could be the normalized decalibration scores for each expert. That is, we define the normalized weights of each expert as the decalibration score for that expert divided by the sum of the calibration scores of all experts. Other concepts of common use, such as optimized decision makers, are also applicable for the dependence calibration score sketched in this video. We have seen during this video that the elicitation of dependence is possible and defined a calibration score that measures the accuracy of experts' assessments of dependence. If you are interested to learn more about the subject, please feel free to contact me. Thank you very much for your attention.